Welcome to the presentation on moments. Moment is a tendency of a force to rotate an object about an axis. So it's a twisting effect of a force on an object. The moment M is equal to force times distance, where F is the magnitude of applied force, and D is basically the distance from the axis of rotation to the point where the force is applied. Distance from axis of rotation to point of applied force. Okay, let's say we have a simply supported beam, which is what we have here. And if you don't know what a simply supported beam is, I recommend you go back to my previous presentation where you can learn to distinguish between the different types of beams. Now let's assume A is our axis of rotation. The twisting effect of force F1, this force here, on the beam is F1 times D1. The effect of the force F1 on the beam is to rotate the beam in that direction. So, and that direction is obviously clockwise, in the clockwise direction. Now let's look at the reaction force RB. Now we're looking at the force here, the reaction force here, and the effect of the force RB on the beam will be RB times the distance from RB to our axis of rotation, which is D1 plus D2. D1 plus D2. Yeah, that should be in bracket as well, by the way. And we can tell that the effect of the force RB on the beam will be to rotate the beam in the anti-clockwise direction. So we're going to call that anti-clockwise. Direction. And that should be clockwise direction. And finally, we're going to look at the effect of the force of the reaction force RA on the beam. Now you can see that the distance of the reaction force RA from our axis of rotation A is 0. So that means this force here, the reaction force, has no effects, has no twisting effects on the beam. Therefore, zero moment basically. So there is no effect. The torque is 0. If you're doing mechanical engineering and you've come across torque, we're basically talking about the same thing here. Now, for a laminar to be in equilibrium, the clockwise moment has to be equal to the anti-clockwise moment. And by the way, this is one of the laws that we have to always stick to. So this is the first one, and the second one is the component of the resultant force in any direction must be 0. So what we're basically saying is the forces acting on the beam, they have to equal to 0. in English, that means the upward forces has to be equal to the downward forces. So maybe I should have a separation here so that we don't get confused. There you go. So we have for the beam, we have, so this is the clockwise moment and this is the anti-clockwise moment. So what we have is F1 D1 is equal to RB times D1 plus D2, and then we can rewrite this equation as F1 D1 minus RB D1 plus D2. That's a 2, by the way. And this, I'll get another color. Now this, that's not too different. I'll get yellow. Well, this is the normal convention when writing down the moment equation, because we sometimes, well, we like to assume that the clockwise moment is positive, it's the positive moment, and the anti-clockwise moment is the negative moment. And if the screen looks way too abstract for you, well, that's because it is. And do not stress too much, because in the next page we are going to, well, put in some numbers. And here we have a simply supported beam, and you have an applied force of 20 Newton acting 0.4 meters from A, and two reaction forces at RA and RB. Now the question is to calculate the reaction forces RA and RB. Well, we know that clockwise moment is equal to anti-clockwise moment, and upward forces is equal to downward forces. And these are our two laws. Every single time we had torque or moment, we have to know these rules. Okay. Now we're going to choose the point A as our axis of rotation, and now let's try to identify the effect of the applied force and the reaction forces on the beam. Now looking at the 20 Newton force, you can tell that it will rotate the beam in that direction, so in a clockwise direction, and the reaction force RB will rotate the beam in that direction, so that's anti and that is clockwise. So you have 20 times 0.4, 20 times the distance from the applied force to the axis of rotation is equal to RB. We don't know the value of RB, that's what we're trying to find out. And the distance of the reaction force to the axis of origin is 0.6 plus 0.4, and that will give us 1. And so we have 20 times 0.4 equal to RB, which should give us 8, and that should be RB, not R8, 8 newtons. Now the next thing is to work out our A. Well, we're going to use the second rule, which says that the upward forces has to be equal to the downward force. That should be honest. So the upward forces equals downward forces, and we're looking at the beam. We know that the upward forces. Let's consider the upward forces first. Those are RA plus RB has to be equal to the downward force, and the downward force is the applied 20 Newton force. And we've already worked out what RB is. That's 8 Newton. So we can substitute 8 Newton into the force equation, plus 8 equal to 20. Ra is equal to 12 newtons. So just to summarize, when you have a problem like this, the first thing you have to do is to choose an axis of rotation. So in this case, we've chosen A, and then work out the reaction force for RB, and then use this rule here to work out the remaining reaction force, in this case RA. And I should have mentioned actually that force is measured in newtons and distance is measured in meters. So that means moment, which is something else, torque, has a unit of newton meters. And with that, I'll end this video, but I'll do a slightly more complicated problem in the next video, so keep an eye out, and thanks for watching.